Hey guys, welcome to Unit 14, Notes B. Today we're going to talk about functional groups. These are areas of special interest, something is a little bit different, that go into the organic molecules. So some of them have halides, so like halogens, some of them have nitrogen, and there's actually quite a few of them that have oxygen. We're going to look at a few of them today. So a functional group, because it would have places where there could be open electrons, not everything's all locked up in bonds like when we were looking at pure hydrocarbons, these are the sites where you're going to have the chemical reactions, and this is going to lead to many mechanisms that you would study in organic chemistry. We're going to stick to just being able to name the molecules based on the different functional groups. So let's look at our first one, where we're going to include our halogens. So we call them halides, kind of based on the name halogen. And a halide would be a hydrocarbon that includes a halogen. And you can tell pretty obviously which prefix would go with which element. Of course, fluoro would be fluorine, chlorine, bromine, and iodine. So now we're just going to use these little prefixes, still using the numbering to tell me where to put this attachment on our base molecule. So it's kind of nice with organic chemistry is once you figure out the patterns of how things work, it's really easy to apply that to something new, like in this case, our halogen. So let's start with the butane, which we know has 4 carbons. And because of the A and E, I know it's a single bond. The 2 tells me where. On my second carbon, I'm going to have an attachment. And the iota tells me which halogen it's going to be. So I'm going to draw my iodine. Now the carbons automatically get filled up with hydrogens, but not your functional groups. If there are hydrogens in functional groups, you actually have to write those hydrogens. It's not okay to leave them off. The assumption with the attachments, these functional groups, by the way, would actually be that they're not surrounded by hydrogens, would actually have the 3 lone pairs around that. But again, we're supposed to kind of understand the octet rule at this point, so we don't even have to draw the dots, but you do not draw dashes. So that would be our 2-iodobutane. So they showed the dots in the first one here, just so you know there aren't hydrogens, but they stopped drawing the dots on the next one too. All right, speaking of our next one, this is a much bigger molecule. So I see here a hexene, not a hexane. So this is going to be a little different than last time. I'm still going to use the hex to figure out how many carbons, which would be 6. But then because of the E and E, I know there's a double bond. And I have to look to the number in front of that name to figure out where to place that double bond. So a 1 would indicate a double bond between 1 and 2, like that. Now I want to look at my attachments here. So I see 2 locators, 2 and 4. So I know I'm going to have an attachment on the second carbon and my 4th carbon. Di, as you've seen before, means that we're going to have 2 of whatever it's attached to. And the bromo, which mean that we're attaching bromine. So Br for each one. So I have the double bond between the first and the second, because it was 1 ene. And I have 2 separate bromines attached to 2 separate locations. Remember, this just means 2 in the total molecule, and it gives those 2 locations. So it's only 1 bromine on each. So this would now just need hydrogens. So be careful that when you have 4 bonds, you don't add hydrogens. Be careful you modify how many hydrogens if you have some extra bonds. We would want to make sure that we comply with the octet rule all the way around. So 2 bromines on our chain here. All right. I want to use this example to show that weird little stick figure thing, just to show that it can still work with even these crazy molecules. So we had 1, 2, 3, 4, 5, 6 carbons. So 1, 2, 3, 4, 5, 6 endpoints on my stick figure. Between the first and second carbon, there's a double bond. So we would draw the extra bond. On the second carbon, there's a bromine. So we would draw the line connecting the stick figure to the bromine. And that's also going to happen on my 4th carbon. So it was 1, 2, 3, 4. It would look like this. Oops, sorry. Again, not drawing the dashes. or, I'm sorry, not drawing the dots on the bromine. Just leave it like that to show where it's attached. Okay, so let's try benzene with some halogen attachments. So benzene, we know, has that six-sided circle with the circle in the middle. Six-sided, and then the circle in the middle. So let's look at our two separate attachments. We have a 2-chloro and a 1-bromo. So this is giving me the location of the bromine and the location of the chlorine. I can see, because these numbers are consecutive, 1, 2, that the bromine and chlorine should be right next to each other, and it really doesn't matter where you put them. I always put one up top, so I'm going to stick with that, and then put the chlorine to the side. But any version of spinning this or flipping this would actually be the same molecule. Keep in mind that does not make it an isomer. It just means that you've changed the orientation of the molecule. So we've got 1-bromo, 2-chloro. All right, so that's going to do it for our halide functional group. On to our second functional group, all about alcohols. So this functional group is going to have an attachment of hydroxide. Whenever you have that hydroxide attachment on a regular chain or a branch chain, you're still going to call it an alcohol. But if that attachment is on what they say here is an aromatic ring, which was our benzene, if we have the OH on benzene, then we call it phenol. So we'll take a look at each. Let's start with our regular alcohols. So notice the ending of the name changed here a bit. The OL instead of just ending with an E. Let's start based on propane, which we've done before. 5 carbons. And then because of the A, propane, all single bonds. The OL tells me that I want to add in this OH group, and I'm going to put it in the second carbon. So I'm going to go into the second carbon and attach an OH group. Then I'm going to fill up the rest of the carbons with their hydrogens. Do not add any dashes to this OH group. You do not even have to show the bond between the O and the H, or the dots on the O. It's assumed that you know how those connections would work because you understand the octet rule. So we're just going to draw in the attachment as an OH and just leave it at that. So I think I had just drawn pentanol, actually. I'm sorry. Prop, P-R-O-P, would actually be 3 carbons. And so then on my second one, I have my OH group. Sorry, mixed up prop and pent. Prop would be 3 carbons. And what I had up there a minute ago would be our pentanol. All right, let's try one with an attachment that's organic and an attachment that's alcohol. So looking at the base word first, bute tells me I have 4 carbons. 1, 2, 3, 4. Bute means 4 carbons, I'm sure this time. The AN tells me I have the single bonds, but this OL would indicate that on the first carbon, I'm going to have the hydroxide group. So on the first carbon, I'm going to add an OH. Now I want to look at my attachment, which will be on the third carbon. So if I made this 1, 2, 3, you got to keep the numbering consistent. So this one's going to have a methyl group, which is just that 1 carbon group. The carbon groups still get the H's, but the hydroxide group would not. So this would be our diagram for, or not our diagram, our structure for the 3-methyl-1-butanol. The structure that they have here is going to look a little bit different, but I want to talk about how it's the same. So they put our OH at the end here, and there's a reason that they did this, that it kind of looks like the C is connected to the O. It kind of just looks more in order. It would look a little weird, especially if I put OH on the left-hand side. It kind of looks like the H is connected to the C, which we know it couldn't be, too many electrons. So this is a very normal thing for an organic chemist to do, and putting the OH on the far side, but that's still going to make this the first carbon, making this the second, this the third, and this the fourth. Remember that we can number backwards. There's nothing wrong with that. So if I make that my first carbon, then my third carbon would be this guy over here, which is getting the methyl group. So it's the exact same molecule as the one I drew a moment ago, just allowing the OH to kind of line up like that, which can be preferable just in the way you're drawing mechanisms and things in the future. Okay, now let's look at a diol. Remember, diene meant 2 double bonds, so diol is just going to mean 2 of the alcohol groups, or 2 of the OH groups. And then the number will tell me where. So let's start by drawing our base molecule, butane, which would have 4 carbons. Now I want to add 2 OHs, and each of them will be, or I'm sorry, one of them will be at the 1, and 2 of them will be, can't talk, I'm sorry. The 2 OH groups will independently be at the first and second position. That's what I'm trying to say. So in the first position, I can add my OH, and then in the second position, I can add my OH. So the question usually comes up right about now, does it really matter whether you're putting them on the top or the bottom? And as we've discussed before, it would be the same molecule, not an isomer, if you changed that. What actually truly happens in the molecule is the Vesper idea where the electrons would be repelling each other, and so they would kind of orient themselves as far apart from each other as possible. But how you're drawing it right now, as long as you've got things connected correctly, I'm good. So the last thing that we have to do to this guy is to add our hydrogens carefully. Not on the OH groups, but on all of the carbons. So this would be our butane diol, or having 2 OH groups. A double alcohol. 1, 2. Notice how the way that they did it, they flipped this HO so it doesn't look like the H is connected to the C. I still think that looks a little bit weird. I would have just drawn it on the bottom, but it really doesn't matter. As long as they're connected in the right place and you're following your numbering systems, you're really drawing the same exact molecule. All right, the last thing that I want to look at with the alcohols is what happens when the OH group actually attaches to the benzene. And then we actually don't call it an alcohol anymore. We call it phenol. So this is where phenol and phenolphthalein, one of our acid-base indicators, gets its name. Phenol actually refers to the OH groups. And there are actually 2 of our OH groups on our benzene. These are phenol pieces. And then there's more to this molecule when you have it in phenolphthalein. So when you attach OH to benzene, it becomes phenol. All right, on to our next functional group, something called an ether. So an ether is going to actually take an oxygen atom and drop it into the chain. Not an attachment or branch off of the chain like our last 2 were, but actually an interruption in the chain. And there are actually 2 naming systems, and in this class we'll give you both of them, one right after the other like this. So I want to explain how both of them can work to give us the name. So let's start with the first one. What do we think meth might mean? Well, meth was that one, let me hold off on the hydrogens. Meth just meant 1 carbon. Then we see oxy, and guess what oxy would represent? Our oxygen. So I'm going to have 1 carbon attached to an oxygen, and then attached to something else. What else? I see meth again. So again, it's just going to be 1 carbon. And notice in this naming system with the ending, you still end it with the A&E. In this class, we're only going to look at single bonded ethers. So it's just going to stay like this. The tricky part is adding the H's. The H's will bond on the carbons, but not the oxygens. And in real life, it would have 2 lone pairs, but we don't have to draw the lone pairs right now. So this would be methoxymethane. Now this is naming it as an ether. So I would kind of have a different starting point. I would start with oxygen and then try to figure out what it's attached to. So what's in front of it would be the 2 attachments. Think of them as branches, right? Here I'm going to have di, so 2, and methyl was the 1 carbon. So I'm going to have 2 1-carbon branches on the ether. And those carbons again get hydrogens, and you end up with the exact same structure. So it's the same exact structure, just whichever way is more helpful to you, makes more sense to you, for you to get there, you're going to end up with the same thing. Here's our methoxy ether. I'm sorry, I just combined the two names. Methoxymethane or dimethyl ether. Okay, let's try one more. And again, I'll walk through it both ways. So meth represented 1 carbon. Oxy would be the oxygen. And now propane would be 3 carbons. 1, 2, 3. The carbons all get hydrogens. The oxygen doesn't, only the carbons. Now let's think about this the other way. If I start with the base idea that it's an ether, I know I have oxygen attached to 2 organic groups. Meth would be a 1 carbon group, and prop would be a 3 carbon group. So I have a methyl and a propyl attachment on my ether. Let me also talk for a second, what if I were given this structure and asked to come up with these names? So it's still following alphabetical order. Notice how M comes before P in either of these namings. So if you're using this version, you would just use meth, but don't use the branch, don't use the YL, oxy, and then prop, and the A and E goes at the end of whatever comes last alphabetically. So this is always the ending of the name. With the ether, you're going to label them both like branches and then just put them in order based on alphabetical order. So I think that's a little easier for me because they're both acting like branches, and then you just put them in alphabetical order. Okay. Let's see what happens if we involve benzene here. So it looks a little bit different in the name depending on which system you're going with. If we're just going to call it benzene, then we would use benzene as our root word. So notice this is one example, one exception, where you're not ending with ANE because you actually just have benzene. It's not some other alkane. Using the branch on an ether, you're going to use the prefix PHEN. Remember, we just looked at phenol, which was where the OH group was attached to benzene. As it turns out, that prefix PHEN actually just means benzene. So if we want a benzene attachment, so something else attached to benzene, then we can say the branch is benzene, phenol. All right, let's draw our molecule now. Meth, again, coming first. So again, I'm starting with 1 carbon. Of course, there are other types of ethers where if you had a different branch here, you would use the right number of carbons. The next thing I get to is the oxy. And then I'm going to draw my benzene, which is that 6-sided figure with the circle in the middle. The carbon still needs hydrogens. The oxygen does not. And then I have my benzene, which does have 6 hydrogens, but it's all represented with that symbol there. You're going to get the same thing for the ether, starting with the oxygen this time. And then you add your methyl group and your phenyl group, and you end up with the same structure. So this is our methylphenyl ether, or methoxybenzene. Same molecule, 2 names. All right, before I move on from ethers, this is not a great example, but I want to show you how you can make a stick figure out of this. Let's go back to this guy. So the oxygen would just go in the chain. So carbon is assumed to be the starting point, and then O would be the second thing. Then we have 1, 2, 3. So this would represent our methyl group, and this would represent 1, 2, 3, our propyl group. So you can just stick the O in the middle, which is why if you have an attachment, you have to draw the line to it so that it doesn't look like it's in the chain. All right, let's go ahead and move on to our next functional group, carboxylic acids. So carboxylic acids are going to have some organic compound where there is a carbon, an oxygen, and a hydroxide. So this is going to act as like 2 separate things in our group. And the best way to describe it is actually just to show you. So let's start with butanoic acid. So I can tell a little bit by the beginning of this butane that I would have 4 carbons, 1, 2, 3, 4. And then whenever you have this oic acid, that tells you you have a functional group, which is going to have a double bonded O and an OH group. This is what we get when we have the enoic acid suffix. Notice that I didn't add the extra C. The C is already part of the butane, but we have to use one of those C's in order to attach the hydroxide and the double bonded O. So you may remember those choo-choo molecules where it was like writing out the C, O's, and there was lots of C's and O's. That happens in order to tell us how to draw the structure without us having to try to guess to it. I can show you what that looks like. Let me just go ahead and add my hydrogens here. So I would have 3 hydrogens on the first one, then 2. This was single bonded, and the carbon already has 4 bonds. So this is our octet rule. So to write this out using that choo-choo format, first we have a C that's attached to 3 H's, CH3. Then we have a C that's attached to 2 H's, CH2. We have another C that's attached to 2 H's, CH2. And then we have this functional group, which is written as COOH. So whenever you see this, the COOH, then you know that you have a carboxylic acid. So it's a way for us to translate what's given at this format of given the formula and translate that directly into its structure without having to try to guess how things are connected and maybe guessing the wrong structural isomer. So it's a way to tell us which isomer we're dealing with. All right. So that's our butanoic acid, based on butane. All right, so what would ethanoic acid be based on then? Of course, eth meaning 2 carbons. So I'm going to have an attachment like this, and then because I see this suffix here, this ending, I know I have that functional group where you have the C that's double bonded to an O and then attached to OH. So make sure that you add your hydrogens to your other carbons, but the carbon that's got the carboxylic acid on it is already going to be busy with all of its bonds. And this would be our ethanoic acid. So notice I still wrote it on the end here. This is another kind of like industry standard thing where you usually draw the OH at the end. That's going to make this the number 1 carbon. So this is going to kind of flip our numbering system on most of our chains. So let's look at some attachments. I have here a 3-methyl pentanoic acid. So let's start by worrying about our main molecule, pentanoic acid. So pent tells me I would have 5 carbons. And then I have this ending, so I have this functional group. So on the end, I'm going to attach the double bonded O and the OH, which means the numbering will start at the end. 1, 2, 3, 4, and then 5. It's numbered backwards when you put the carboxylic acid at the end. So that's going to dictate where my attachment goes. So I have a methyl attachment this time, which was that 1 carbon branch that I want to put on the 3rd carbon. It's going to get dashes just the same as all the rest of them. Let me just get my numbers out of the way. But just remember that the carboxylic acid carbon is already full. So this would be our 3-methyl pentanoic acid. All right. Notice on this one, we would have gotten lucky either way because the 3 is in the middle of the 5 carbons. So even if we did number 1, 2, 3 or 1, 2, 3, we still end up with the same carbon. So I have a question then. If this were actually 4-methyl pentanoic acid, would that carbon move closer to the carboxylic acid group or further away from it. It would actually move over, since this was my first carbon, second, third, the fourth carbon would be the one that's further from the carboxylic acid group. The carboxylic acid group always being the number 1 carbon. Okay. So now let's end the carboxylic acid groups by tying it back to benzene. What does benzene look like with this functional group for it? So I want to challenge you to try to draw a benzene molecule. Remember our 6-sided figure with the circle in the middle? Try to draw that and find a way to attach the double bonded O and the OH group without violating the octet rule. It's not that easy. When we draw our benzene structure, remember what we're really representing is that every other bond here is a double bond, meaning every carbon that we have drawn here already has 3 bonds or 6 electrons. So if I added a double bonded O and an OH, I would end up with 1, 2, 3, 4, 5, 6 bonds, or 12 electrons, a definite violation of the octet rule. Sometimes people try to break it up, which would still violate the octet rule with the double bonded O, and you wouldn't call it a carboxylic acid anymore. The only solution is that we need another carbon, something that can carry the double bonded O and the OH. And notice how that extra carbon would already have 4 bonds as well. The thing is, notice there's not any acknowledgement of that extra carbon in the name. We don't add anything to show that we have to add the extra carbon. It's expected that because you understand the octet rule, you would understand that that's the only way to get a carboxylic acid group on the benzene. And so this is the only time where you would add an extra carbon to whatever the molecule is to carry the double bonded O and OH. This is only for benzene to make benzenoic acid. All of the other carboxylic acids just tag on to the carbon that's already there. Benzenoic acid. All right, now let's shift gears from oxygen-based functional groups to nitrogen-based functional groups. These are all going to be derivatives or things that come from ammonia. So the basic structure of ammonia is this, where we have 3 hydrogens attached to the nitrogen by all single bonds, and then on one area you have a single bond, a single lone pair. So that lone pair is actually in the s orbital, and these are bonding p orbitals. The reason I bring this up is not to rehatch nightmares from writing electron configurations, but to tell you that there is a reason why we are only going to be using bonds in sets of 3 for the nitrogen. Meaning that if I want to add another group, I'm going to have to remove a nitrogen. That's going to be the mechanism of how this set of derivatives work. So the name to say that you have some version of ammonia is called amine. So that tells me I want to start with my ammonia structure, but I want to add a methyl group this time. So as we've seen a bunch of times now, we have that methyl group means 1 carbon. If I'm going to bring in a carbon, then I'm going to have to remove a hydrogen. Just consider that lone pair off limits. You can only swap out. So you're swapping out the hydrogen for a carbon, but that methyl group, that carbon, is going to have the hydrogens all surrounding it. So always having to draw the dashes on the carbon, but always having to write the H's on the functional group. So this is really how you would write this structure, even though these are also H's. And if it makes you feel better to write the H's because it looks kind of weird half and half, that's fine. But definitely make sure you always write them on the functional group. So we've got our methyl group attached to the base ammonia molecule. What if I wanted 3 methyl groups? So let's start with the amine, which was the nitrogen attached to 3 hydrogens. And then we have our off-limits lone pair. Methyl branches, those 1 carbon branches, need to be placed on this molecule. And each time I put 1 methyl group in, I have to take away 1 hydrogen. Remember, we're only swapping out. So here's the catch on this one. This needs to happen 3 times. So each time that I put in a carbon, I have to replace a hydrogen. That lone pair is off limits. Now each of the carbons needs its hydrogen set, which would be just completely surrounding it, and then we still have the nitrogen in the middle. So that would be our methyl, or trimethyl in this case, amine. All right. So now let's look at using that NH as a smaller part of a bigger molecule. When I was naming amines, let me go, back. When I was naming the amines, the nitrogen was kind of in the center of the molecule, whereas when I'm using amino, it's going to be very similar, having to come from the NH3 group, but whatever I have at the end of the name would always be the base molecule. So in this case, I have butane, and but means 4, and the ane for our single bonds. That's my base molecule. But now I want to attach an amino group, or a version of the NH3. So the 2, the number in the front, still always connects to where to place the attachment. So on my second carbon, I want to place that nitrogen-based group. So the ammonia was NH3, but could the carbon come in as an additional attachment, meaning no lone pairs? Well, no, we said the lone pairs were off limit, or the lone pair was off limits. So what it would have to do instead is to replace one of the hydrogens, leaving just NH2. And as it turns out, we don't have to draw this out any more than we have to draw out the OH connections. We can just label the attachment as NH2. You just have to know it's NH2, not NH3. One of the H's being lost as it connected to the hydrocarbon chain. The hydrocarbon chain, by the way, is still needing its hydrogens, which we can draw as dashes, but you have to write the H's in the functional groups. So this would be our structure for the 2-aminobutane. Just being able to write the NH2. All right, let's try a little bit of a bigger molecule here. We have cyclohexane as our base molecule. So that's very similar to benzene, but without the circle, it's just cyclohexane. If I drew the circle in there, it would be benzene. Now let's look at our attachments. The first attachment I see is a 1-amino. So amino would be my version of NH3, but remember you would have to lose an H to join up with the cyclohexane. So I'm gonna add that in as just NH2. And then I have a 3-propyl group. So if I've decided that this is my number 1 carbon, then I have to skip a spot. Notice how there's no number 2 up here in order to get to a 3rd carbon. And it really doesn't matter which direction you go as long as you are 1 carbon away. And then I'm going to add my propyl group, which would be a chain of 3 carbons. So I would give my carbons their attachments, their hydrogens, but I have to draw in the hydrogens, or write in the hydrogens when I write NH2. And that would be my structure for 1-amino, 3-propyl, cyclohexane. You just got to be careful that you're using NH2 and not NH3 when you attach it to the hydrocarbon chain. There we go. All right, so the last thing that we've been doing is attaching the attachments, the functional groups, to benzene. So when you do that for the NH2, we call it aniline. So aniline would just represent this exact structure where you have the benzene attached to the NH2. Just like when you say phenol, you're referring to the benzene attached to the alcohol group, OH. So you have to know your names for your benzene derivatives. Aniline would be benzene attached to NH2. We can also put some attachments on aniline. So seeing this tells me I have the base molecule where benzene is attached to NH2. That's going to make this the number 1 carbon. So when I add my other attachments here, I want to go further away. And it doesn't matter whether you go 1, 2, 3, 4, like which direction you go. So if I just keep going clockwise, my third carbon and my fifth carbon would be 1 carbon away. This is going to spread out. What am I attaching here? 2 chloro. So that would be 2 chlorines, not on each, but 2 total. 1 at the 3 and 1 at the 5. So I would draw in chlorine and another chlorine. So that would be our structure. No hydrogens on the halides, remember? Just having the Cl written in the right place. There we go. So having them spaced apart to show there's the 3 and the 5 a space away from the aniline. By definition, number 1 carbon, just like with the carboxylic acid, wherever you use that functional group is the number 1 carbon. All right, let's try one more that's going to look a little bit different. I want to try approaching it strategically the exact same way. So aniline, my base molecule, would be my starting point. So again, I'm going to draw that 6-sided figure with the circle in the middle of it and pick a carbon to be my number 1 carbon holding the NH2 group. Now I want to look at my attachments. So let's think about this logically. I know the meth means 1 carbon. I know di means there's 2 total, 2 separate 1 carbon sets in the molecule, and that these are going to be branches. Now normally the branches are located, or their location is given, by the numbers in the front. The numbers telling you which number carbon to use. But it's also possible to attach things to something that's not carbon. What do you think the N might stand for in this case? Well, it would have to stand for our nitrogen here. And if we're going to attach a carbon group, we're going to have to lose a hydrogen. And the fact that I have to attach 2 carbon groups means I'm going to lose both carbons. And those carbons would always be full of hydrogens, but not the nitrogen. Remember, its lone pair is off limits. So that would be our structure here for NN-dimethyl. Instead of using numbers, using the N to show the attachments are actually on the nitrogen. Kind of interesting way to do it. And so we have N attached to 2 separate carbons, NN-dimethyl, all based on aniline, or our benzene derivative. All right, guys, that's going to do it for Unit 14, Notes B, our very last set of notes. Congratulations, you made it through Honors Chemistry.